Bonjour à tous, comment ça va? Bien? N'est pas fatigué après toujours? Non? C'est bon? Euh, Comment vous probablement détectez, je parlais en français n'est pas bien. Alors, je continue en anglais, OK? Cool. So, my name is Evgeny Mandrikov. I don't speak French very well. Today we are going to talk about bytecode pattern matching. Before that, I need to do a usual disclaimer that whatever I say is just my opinion, not my employers. They can only dream that they own my opinion. Nevertheless, I work in a great company, SonarSource. They create great products, SonarLint, SonarCube, SonarCloud. If you want to know more about these products, please come to the booth. And this talk is not going to be about them. It's going to be about something more interesting. So we're going to talk about bytecode and all this. Why? Because in my spare time, I work on such great project as JaCoCo and plugin ECLEMMA, which integrates JaCoCo into the Eclipse. Before we start, just a little bit of brief history. Long time ago, there was a great Java 5. In 2004, it was released. And there was a nice coverage library for Java 5 called Emma. But there was no other tooling, so there was no plugin for Eclipse. And at some moment of time, closer to the Java 6 release, my friend Mark Hoffman wrote such plugin called ECLEMMA, which is a combination of two words, Emma and Eclipse. Later on, he realized that Emma doesn't evolve, so there is a need to develop a new coverage library, and here is how JaCoCo was born. A combination of three words, Java code coverage, pretty simple. Since then, a lot of time passed. There was second version of ECLEMMA based on JaCoCo. Now ECLEMMA is part of Eclipse Foundation. It's official Eclipse project. A lot of other Java versions were released in the meantime. It starts to be quite hard to catch up with all this. Bytecode changes, Java language evolves, and we are going to see why for JaCoCo it's quite hard to catch up with all this. Important note is that JaCoCo works only on a bytecode level. So it doesn't require actually existence of a source code. It recognizes the bytecode. If you don't have a source code, you still can have a coverage metrics. Let's move forward. It is tested on wide range of JDK versions, on 6.5, half because we also test on early access builds of 11, which is not yet released. Why? Again, because Java compiler changes, JDK changes, we need to catch all those changes. And while we do such a testing, we actually find not only issues in JaCoCo, we also find issues in JDK. I would even say that we mainly find issues in JDK, but not in JaCoCo. And apparently, okay, we are in top of open source contributors of bugs into OpenJDK tracker. Boom. And now a real disclaimer. Sorry, but there will be some internals of JVM. Sorry, we are going to talk a strong language bytecode. If you are not ready, door is just over there. And I will try to do a little bit of violence for your brain. Sorry for that. Again, there is another door just over there. Okay, let's start. As a warm-up, let's talk about something pretty simple. We're going to talk about synthetic constructs in the bytecode. We're going to talk about something unnatural, which does not exist in your source code, but exists in your bytecode, in your class files, in the result of compilation of your source code. So as a little warm-up, maybe you know what's so special about such simple source code. What will be in the bytecode? Wake up, you can shout loudly. Yes, it is implicitly extending object. Just here there is extend object because every class in Java should extend something, and except object. Object doesn't extend anything. So every class by default extends Java lang object. Something else? Default constructor. Yes, there is implicit default constructor. So let's try to see how it's going to work for more complex examples. Let's try to see this default constructor. So I do have this little example. Oops. Yeah. So here is class Java, class fun. Let's compile it. If you do not know what is in the bytecode, you can easily get it. There is such a command javap. Here is its usage. It can basically show you the bytecode of some class file. So let's have a look. -v verbose, -p show privates, etc., etc. So basically, javap -v -p show me pretty much everything. Oops, what's wrong? Okay, javap -v. Bam. This is such a simple class which contains almost nothing. Was decompiled into monster like this. Let's check what is in this monster. There is a little bit of meta information. What is MD5 checksum, from which source file it was compiled, major minor version, so which GDK is targeting, some flags. We are not going to focus on this, and constant pool. Constant pool contains all the constants referenced by other bytecode instructions in the source code later on. So we can see here references to javalang object, javalang object.init, which is a constructor of javalang object. We can see the class name, etc., etc. Then here is the content of the class itself, and we can see that there is a method which is actually a constructor. So the constructor that was generated, which we do not have in the source code, and here is its code. In its code, we can see that something strange happens, but we probably can guess by this method name what happens. It's actually a call of super constructor, and that's it. So coming back, this is how it looks. If you do not write your constructor, the implicit one is going to be generated for you, and it contains only one call of a super constructor. There is an interesting word on this slide, synthetic. If you will open Java language specification, yes, in a part about bytecode, we could find that there is a special flag, a special annotation for a constructions that do not appear in the source code. Such constructions called synthetic, such constructions are marked by this flag, this attribute. But there is few exceptions. One of those exceptions is default constructor. Okay. Let's move on. Do you know some other examples of a similar construction which is generated by compiler but is not marked as synthetic in the bytecode? Any ideas? Okay, let's move on. It's pretty simple. It's actually enums. If we define enum with some constants, we would automatically get an access to a method value of on enum and to method values. They're not marked as synthetic. Let's check this. So here is example. It contains, oops. Okay, it contains enum. It contains some method. We print the access value of. Let's compile it. Let's decompile it. So again, a lot of something, a big constant pool. We do not focus on it. Here is again constructor that was generated for enum. Here is our method, fun. Here is some static initialization, which actually initializes all the constants in the enum. And here is two additional methods, values and value of. Any idea why they're not marked as synthetic? Why in the Java language specification there is synthetic attribute, but some synthetically generated constructs are not marked as synthetic? Yeah, let's say for the IDE, more or less for the IDE. Actually, it's only compiler who is allowed to call synthetic constructions. From the user source code, you're not supposed to have any access to the synthetics. That's it. However, in those two examples, default implicit constructor and value of and values methods, user should have ability to call those methods. So they're not marked as synthetics. But okay, then logical question. What is actually marked as synthetic? Do you know the examples of synthetics? Remy, I know that you know. Go on. Yes, perfect. So this is synthetic. Not really fields, but pretty similar example. We have an inner class. It contains a private constructor, and it's called fun. So let's make some new fun. What's going on here? Let's check. So here we have the same example. Let's compile it. Let's have a look on the result. In the result, we have a constructor of a class example. We have method fun. Okay, it exists in the source code. We have a call of example fun class. But what is interesting is that this call contains actually two arguments. And here we can see that on a stack, there will be two arguments. Second one is going to be null. The second argument is quite interesting. It's named example $1. We do not have such class, do we? Let's check what we have after compilation. Actually, we do have. So here is our source. Here is our outer class. Here is our inner class. And here is example $1. Let's check what is this one. And bam, we finally see the synthetic attribute. It's synthetically generated class. Interestingly, this time it has no constructors. It is empty. Why this class is there? Because actually, while Java language easily allows you to access private members that are within the same source file, Java virtual machine doesn't have a very good notion of nesting. And by default, it doesn't allow access to the private members. It doesn't know how those two classes, example fun and example, correspond to each other. Hopefully, this is going to change soon with nestmates. While it is not changed, we need to somehow align the Java language and Java virtual machine rules. In order to do so, Java compiler is gonna generate in your inner class. So let's have a look on the inner class. It's gonna generate in your inner class. In your inner class, it's gonna generate a special constructor. This constructor now marked as synthetic. You're not supposed to call it, but the bytecode will call it. And we've seen this code. This constructor is no more private. So here is constructor that you wrote. It is private. And here is constructor which Java compiler generated. It's synthetic and it is not private. This constructor allows the example class to actually call this synthetic constructor. This synthetic constructor is going to call the real one. This allows to instantiate a class whose constructor is private. Okay, we finally found one example of synthetic constructions thanks to JavaP. Indeed, another example of synthetic construction is access to the private fields. Let's check this one. So, pretty simple example. We have a private field declared in outer class. We have an inner class. In an inner class, we do access to the private field of an outer. Let's compile. Now that we know that compiler generates a lot of classes, let's have a look what was generated. Okay, this time nothing additional was generated, just outer class and just inner class. But let's have a look on what is actually inside. In the outer class, we now have pretty interesting constructions. We have a field, it's private. We have implicit constructor. And we have another synthetic construction, which is synthetic method with the name access blah, blah, blah something. This is so-called synthetic accessor. Again, we need to align the rules a little bit. By default, we can't access the private field of some class. So here is a public accessor of this field. And what it does, it gets a value of a field. Within this class, it is allowed because class itself can access its private field. Then it does increment, saves the value. If you look now on our inner, we see that method increment actually doesn't perform any increment. It simply invokes the accessor method which performs actual increment. This is another example of actually marked synthetic construction. Again. Another example of synthetic construction, which might be not so obvious, it's actually lambdas. So if we have some lambda in our code, If we have a lambda like this, pretty simple lambda, let's exec some runnable, let's exec some fun. Then if we compile, we can't compile. Why? Probably because I am on older version. So let's pick something newer. If we compile lambda, we're gonna see a lot of stuff. In particular, so again, constant pool, big constant pool, implicitly generated constructor, our exec method, nothing interesting. Our method fun, something interesting. There is some interesting constructions start to appear. And bam, synthetically generated method again. And name of this method is lambda fun blah, blah, blah something. If we will look on the line numbers of this method, we might notice that actually this line number is exactly the line of a lambda. If we will write something inside of a lambda, for example, hello the box, and we decompile again, then in this synthetically generated class, we are going to see hello devox, output of this. So actual body of a lambda is compiled into a special method, so-called bootstrap method. This method called synthetic. Bam. Let's move on. So let's check if you're really ready now. Let's check if you warm it up enough for something more serious. So here is another example of source code. Any idea what is happening in the bytecode? What could happen? Is there such bytecode instruction as assert? What depends on my options? Okay, could you please tell me how I'm gonna switch? No, okay. No, actually, okay. Rule of thumb, we do not know, let's have a look. Pretty simple. Stack Overflow, no. Why Stack Overflow? We can write and we can compile. Now we know how to decompile. So, assert. Let's compile. Bam. Let's decompile a lot. Here is our method fun. It accepts Boolean. And here is the body. In this body, there is nothing so special, except there is access to some field in the current class. And this field is called assertions disabled. And then there is branch. In the source code, we do not have branch. This branch basically verifies what's the value of this field, whether assertions enabled or not. Then after verification, it actually loads the value of Boolean argument. It checks the value of the Boolean argument. And then, depending on this value, it either throws an exception, either don't. Pretty simple. The reason is actually there is no compiler flag to enable or disable assertions. But there is a runtime flag. At a runtime, you can have enable assertions or disable assertions at a runtime. Since it is in runtime, you need to compile for the both variants of the runtime. Let's come back to our decompiled code. The machinery which decides whether assertions enabled for some specific class or not is pretty heavy. And it will be a mistake to, on each call of a method that contains an assertion, or if your assertion is inside of a loop, for example, it will be a mistake to go to this runtime, to heavy runtime, and to ask it, please check whether assertions enabled or not. It's much cheaper to have a field, initialize this field once in a static initializer, which is, again, we didn't write, but it got generated. And by the way, again, it's not marked as synthetic, but it's got generated. And this is something which is not written in Java language specification. But this happens. And in this static initializer, we go to the runtime. We ask the runtime whether assertions enabled for the given class, and we store the value in the field. This provides to this class pretty cheap access to the status. That's it. So now I hope that you are really warmed up. I hope you've seen quite a lot and you're ready to see more hardcore examples. Are you? Before we go into them, let's make a note while this is important. For the code coverage tool that operates only on the bytecode, it's very important to know all such tricky cases, because otherwise users gonna come back and say, look, your coverage tool says that I have 4 branches not covered. How it's possible? Here is my source code. There is no branches at all. And it was quite of a challenge. It was a challenge of previous year to implement some filters for some constructions, to filter them out so that the coverage report as much as possible corresponds to the source report. Let's have a look on the such examples where this was important to adjust. You know that at some moment of time, switch on string appeared in Java. There is no such construction as switch on string in the bytecode. How we can compile this into the bytecode, which can switch only on integers? What do we do? Loudly. On what? It will be quite expensive to switch on characters if your characters are quite big. Hash code. We switch on hash code. Let's have a look. So here is our source code. We compile. We decompile. Let's have a look on our fun. So we load argument, then we invoke method hashcode, then we switch on hashcode. Depending on the hashcode, we arrive either here, either a little bit further. And what we do on these constructions, we actually need to indeed check an equality. So first we do a fast switch on the hashcode. Hashcode is anyway cached for strings, so it's pretty cheap operation. With a good probability, if our strings have different hashcodes, with a good probability, we will already end up in the correct case. But we still need to verify that this is a correct case because multiple strings could have the same hashcode. So we call equals to be sure. And here we have two equals actually that verify correctness. And here it actually happened that these two strings, they have exactly the same hashcode. So here is the same hashcode for two strings, and this code is gonna first do equals on one string. If it's not this one, let's do equals on another. Bam. Cool. That's great. Either this was already reported, either let's report this to the GDK. Thank you. Thank you. Okay, it was not promised, but we even found a bug in Java compiler. Let's move forward. We have few more cases to go and not so much time. Oh no, actually not so many cases. Finally, we came to finally. So we are nearly the end. What's so special about finally in a Java language? Forget about bytecode. It should be executed on all possible exit paths from your try catch block, on all possible paths. Whether you catch exception, whether you don't catch exception, whether you immediately return from the method, whether you break an outer loop or whatever, always should be executed. Let's have a look how this is implemented actually. So we have a pretty simple try finally. Try calls a method, finally calls a method. Two calls of a method, just two. Let's compile. Okay, here is our fun. What we can see, call of a method, call of a method, call of a method. We have two, why three? On the bytecode, the only thing to deal with exceptions is so-called exception table. It simply says if exception of this type happened in a range of instructions from this one to this one, then please jump to exception handler at this instruction to handle this exception. And in this exception table, there is no notion of finally. So in order to ensure that finally block is going to be executed on all possible exit paths of our try catch block, we actually need to duplicate finally. How we can see this? Let's do a little trick. Let's add a parameter. So now we can actually distinguish those method calls. One of them contains argument body, and then another one contains argument finally. And now we can see that there is 2 copies of a call which has argument finally. Why 2 copies? One copy exists at the end of try block, so on non-exceptional path, and another one exists vice versa. So this one on non-exceptional path, and the other one on exceptional path. We can even check this. So exception table covers from 0 to 5. This is non-exceptional path. This is a body of try. And target is 13. So this is a catch. This is exceptional handler. So in exceptional handler, we have one duplicate, and here we also have another duplicate. Knowing this, you might do pretty interesting things. Finally, why not? How many copies we're gonna have? Okay, we can check. I don't want to count. You can count if you want, but I don't want to count. This is pretty interesting because this grows quite fast. And you know that in JVM there is a limit on a bytecode size of a method. So if you're using such nesting, it's pretty easy to reach this limit quickly. At home, as a little bit of a homework, you might do an experiment. How many nesting of try finally do we need in order to reach the limit of a method size? Well, it was finally, but it's not the end. We have a little bit more. In some version of Java, in which one? Try with resources was introduced? 7. Try with resources. How we could implement it on the bytecode level? We already know how to implement try finally. We already have exception table for try catch. Yes, we will just duplicate some bytecode. We will just have some finally, and we will close the resources. In fact, the Java language specification explicitly says that try with resources, blah blah blah, is equivalent to the execution of the following code. And this following code, okay, it contains some placeholders, but briefly, there is finally, and this finally contains clause of resources. Also, we know that in Java 7 was introduced so-called suppressed exceptions. So if exception happened and then another exception happened when we've been closing the resource, we need to use the method addSuppressed to have on the stack trace 2 exceptions. So here is addSuppressed. And so we need actually to handle 2 cases. One case is when exception was thrown, another case when exception was not thrown. So here's the, if exception was not was thrown, then we need to use addSuppressed. If exception was not thrown, then we can just close, and if exception happens, it can just bubble up. Let's check how it looks. doesn't look good. So what do we have here? We have some resource. It's closable, so it's possible to use it in try with resources. And here is our try with resource. Pretty simple. Let's decompile. And the method fun is actually quite big. It indeed contains add suppressed. It indeed contains closing of resource. It indeed contains copies of add suppressed because all this happens in a finally. So there is a copy of this finally again, one on exceptional pass, another one on non-exceptional pass. Can we verify that Java compiler produces something like this? Why not? We have another example, which is exactly from Java language specification. Okay, we can write try with resources exactly as written in Java language specification. So we have a Java compiler version 7. Before we compile handwritten variant, let me save output of the real try with resources of decompiled version somewhere. Now let's compile handwritten variant. Let's decompile the handwritten variant. Handwritten variant has the same name as non-handwritten. It has a name example, so I'm not cheating. I'm not picking the same class file. It was ever written. Let's do a diff. This is our diff. In this diff, there is only differences which correspond to line number table, because obviously the amount of lines increased. And that's it. The rest is the same between two class files. So actually, indeed, Java compiler implements try with resources like this. If you will remember our filters and code coverage tool, this actually means that if you implement a filter for try with resources, which filters out all those branches that we do not want to see in the coverage reports because we never wrote them, we are going to just trust the compiler. This actually means that it's possible to trick our coverage tool. If we would write such source code, now it's possible to say, my source code is filtered out, whereas I covered it, I wrote it. Unfortunately, there is no silver bullet because you can't actually you can't solve the problem of the compilation. It is possible to have two source codes which do compile into the same bytecode. Reverse transformation is quite hard. Can we have something interesting on this example but more? Yes, we actually can. We are not going to look on the bytecode because it's going to be hard, but let's look on the source code. We know that this is nearly the bytecode. What is interesting here is we know that the finally part, this one, is duplicated. It is duplicated into the body, and it is duplicated into the catch. However, we could notice that on some paths, those conditions are impossible. In particular, this one is not possible at all, because we can statically prove that we did initialization of resource, and we did it far before the try catch. So actually, this is dead code. It exists in the bytecode. The second one, if we will put it into as a duplicate into the catch, it is dead code. In the catch, we can prove that there is exception always. It can't be null. Here it is. So at the end, Java 7 compiler was not so smart, and it was heavily increasing the bytecode when you was using try with resources. In Java 8, story was slightly changed. Java compiler became more smarter. For example, it started to avoid resource null checks when it can prove that resource is not null. So basically, when you use new, if you use some method calls, and it's harder to prove that it's not null, so it still uses a null check. It also becomes smarter in a sense that this logic is always the same. All this logic is always the same. So if you have a lot of try with resources statements, then why not extract this logic in some helper method? Again, it will be, let's say, your little home task. If you will duplicate in original example with try with resources, if you will just duplicate this method, I don't know, 14 times, for example, you will see that Java compiler of JDK8 and greater is gonna generate a special helper method which closes the resources in order to reduce the duplicates. Unfortunately, even this was not removing the dead code. Like, again, primary exception is not null on exceptional path. It's super stupid to check it there. And this was finally fixed in JDK11. Let's have a look. Oops, we don't have it, but we should. Let's have a look on early access build of JDK11. So, early access build. Let's remove all class files. Let's decompile. Oops. It won't be incredibly obvious, but or let's hope it will be. There is no more null checks. There is no ifs in this bytecode. So in JDK11, compiler become really smart. It can prove that, okay, we initialize the resource, it's never null. And then, when doing a duplication of a finally for try with resources, in one of those duplicates, we do not need to have a null check. So it is omitted. Why it was interesting for code coverage tool? Well, we implemented filter. This worked perfectly for 7, 8, 9, 10. In 11, it got broken. We're gonna fix that. It's not a big problem, but it's quite hard to adapt to the change and to the changes in the compiler. And that's again why we need to test on a wide range of the compilers how all this behaves. So at the end, if this was interesting, please do a few little home exercises. If this was interesting, please get involved. Let's have fun together. Now you, into both projects, now you know far more than any average user of Java code coverage library. So don't hesitate, join our user mailing list and help answer some questions from the users that know less than you. Stack Overflow is the same. There is tons of questions on various stacks. And that's the end.